Hey, have you ever really stopped to think about the screen you're looking at right now? It's so much more than just a piece of glass. It's an absolute marvel of precision manufacturing. We're going to go on a journey from this huge slab of what's called mother glass all the way down to the trillions of perfectly aligned liquid crystals that make up your display. Let's break down the incredible story of how these things are actually made.
So let's start with a little context, right? The average TV people are buying today is over 40 inches. I mean, we just take these massive, super high-res screens for granted. But it wasn't that long ago, a couple of decades maybe, that a screen this big would have been crazy expensive, a total luxury. So, what happened? What changed? And that really is the question, isn't it? How do we go from that to, well, this? How did these giant, beautiful screens get so big and, more importantly, so affordable? Well, it's not magic. It's a story of some serious manufacturing genius that all starts with a very simple and a very, very big idea. So here it is. The secret to making screens cheaper wasn't some super complex new chemistry, not at first anyway. It all started with just making the raw material, the glass itself, way, way bigger. I mean, enormously larger. This was the first huge breakthrough that started driving down costs and finally got those big TVs into our living rooms.
And the solution was something the industry calls mother glass. The idea was, instead of making one screen at a time, which is super inefficient, manufacturers started creating these gigantic sheets of specialized glass. And they were so big, you could cut many, many individual screens from just a single piece. The best way to think about it? It's literally like a giant cookie sheet for displays.
And this chart right here really shows you the insane efficiency gains. A Generation 6 mother glass, okay, that could give you maybe 4 40-inch panels. Then you get to Generation 8 and you've doubled it to 8, but then just look at Generation 10. You're getting a staggering 18 panels from a single sheet of glass. It's just simple economics, right? The more cookies you can get from one sheet of dough, the cheaper each cookie is. Same idea here.
Okay, but of course, it's not just a single sheet of glass. That'd be too easy. Every single LCD screen is actually this super complex sandwich made of two main layers of glass. They're called substrates. And each half of that sandwich has to be prepared with just incredible, microscopic care.
So here's a quick roadmap for how that whole sandwich gets made. First, you've got to apply something called an alignment layer. Then, you apply a sealant, you fill it up with a liquid crystal, you assemble the two glass substrates together, and finally, you cut that giant mother glass into individual screens. So let's dive in at the beginning, with that alignment layer. So everything really kicks off with this alignment layer. It's this incredibly thin film. We're talking microscopic, and it's coated right onto the glass. Its one and only job is to act as a guide. It's like a traffic cop telling trillions of tiny liquid crystal molecules exactly which way to face. And believe me, that control is absolutely everything.
So how do you even apply this super critical, super thin layer? Well, the traditional way was something called roll printing, which is basically just a very, very high-tech paint roller. But the modern method? That's inkjet printing. It's a non-contact process, which is a huge deal. And it's so much more accurate that it cuts material waste by about half. Okay, so we've got the alignment layer on the glass. Great, but how do you actually use it to tell those liquid crystals where to go? This is where the whole process gets truly ingenious. You are not going to believe this, but the main technique for doing this has been around since 1911. Seriously, it's called the rubbing method. And when you hear what it is, it sounds almost shockingly low-tech. But this simple idea was absolutely essential to the industry for over 100 years.
Yeah, the rubbing method is, well, it's exactly what it sounds like. You have a roller that's covered in this special cloth, and it literally just rubs against the alignment layer. That physical friction creates these unbelievably small parallel grooves on the surface. So then, when you add the liquid crystals, they just naturally fall into those grooves, like logs in a river, all pointing in the same direction.
But, as you can probably guess, actually rubbing something all over your microscopic surface has some pretty serious drawbacks. For one, it creates dust, which is an absolute killer in a clean room. It can also cause electrostatic discharge, a tiny zap of static electricity that can just fry the delicate little transistors on the glass. And honestly, its precision just isn't that great, and that ultimately limits the quality of the picture you see. So as we all started demanding better and better screens, manufacturers knew they needed a better way to do this, and the solution they found wasn't mechanical at all. It was light. This amazing process is called photo alignment. So instead of rubbing anything, manufacturers shine a very specific kind of polarized UV light onto a special light-sensitive alignment layer.
The light itself is what does all the work. It causes a chemical reaction that reorients the surface molecules, creating that perfect template. And the best part? No dust, no static, no physical contact whatsoever. It's just clean.
And the benefits here are just huge. I mean, you get way less contamination and way less damage to the screen. The alignment is so much more uniform, which is how we get those really deep, inky blacks and the super high contrast ratios we love in modern displays. It even enables these advanced tricks like multi-domain pixels, which is just a fancy way of saying it's the reason you can look at your screen from way off to the side without all the colors getting weird and washed out.
Okay, so our two glass halves of the sandwich are prepped and ready. The alignment layers are perfect. Now comes the next big challenge. How in the world do you get the liquid part of the liquid crystal display in between them, especially when you're working with a mother glass the size of a garage door? Well, the old method was called vacuum filling. You'd basically seal up 3 sides of the screen sandwich, dip the open edge into a bath of liquid crystal, and just let a vacuum slowly suck the liquid in. The problem? It was unbelievably slow. We're talking it could take days for just one 40-inch panel. Plus, it wasted a ton of really expensive material. It was a huge, huge bottleneck. So the breakthrough that changed everything was a totally different idea: one-drop filling. Now, with one-drop filling, or ODF, you dispense the exact amount of liquid crystal needed right onto one of the glass sheets before you even put the sandwich together. Then, in a vacuum chamber, you bring the second sheet down right on top of it, squishing the liquid out perfectly and sealing the whole thing up. This single innovation took a process that used to last for days and turned it into one that takes just a few minutes. This, right here, was the key that finally unlocked mass production for big screen TVs. All right, we're almost there. The two halves are prepared, the liquid crystal is sealed inside, and our massive glass sandwich is fully assembled. Now it's time for the final transformation, where we see how this thing actually becomes the screen we all recognize. So once the two big sheets of glass are bonded together, the whole mother glass gets scored and then precisely broken into all those individual screens. Then they get a serious cleaning with high-pressure water to blast off any tiny glass particles. And the final, critical step: polarizing films are attached to both the front and the back. You can think of these like microscopic Venetian blinds. They work together with the liquid crystals to either block light or let it pass through, and that's literally how an image is formed. And that really brings our whole journey full circle. From that single, colossal sheet of mother glass, all the way down to the perfectly crafted display you have in your living room or even in the palm of your hand. Every single screen started out as just one small section of a much, much larger whole. So the next time you look at your screen, maybe you'll remember the incredible story behind it, this amazing dance of light, liquid, and mind-boggling microscopic precision. The process we just walked through is what made all of today's displays possible. Which really makes you wonder, right? What kind of insane new breakthroughs are we going to need to create the screens of tomorrow?